I was a challenge.
Bye.
Have a wonderful Thanksgiving.
You too, take care. I will be collecting the lab report from you when developing. Want to staple it up perhaps? Make sure your name's out there.
What exactly is this?
Huh? I don't know, somebody left it there.
I'm so glad we're almost at winter, or no.
No, we're not at winter break. We're not even at Thanksgiving break yet. See that clock? It doesn't say 2:06. When it says 2:06, that's when Thanksgiving break begins. Notice the clock is off. You guys can tell time, but the idiots that run this school cannot.
I said we're close to it. Really?
I think we were just traded for a minute. He gave away Eddie Lacy. But Eddie Lacy is yeah, he's like, he got one. Hey RJ, what? You know Charlie needed
Luke.
Saw that. Yeah. Do you know? What? It's on that. We didn't say a single word to each other. Dude, okay. You and Luke? Yeah, you're so very nice. Really? Like why? I was wondering. I don't feel like I got better than the
We'll be collecting the lab report when developing. Keep in mind that the period does not end until 2:06. Thanksgiving break. Make sure you have it.
Not making a mistake.
Aaron. That's what I said.
Every single possible item of
Did you wear your jersey over your?
No, I changed.
I'm just kidding. You know, I don't know.
Actually, I believe they already took it.
Oh, you think so?
Including the
Perfect.
It's just easier if you do it that way, it's just like it out.
Yeah, it's also a 5.
Here's on Google Docs. Google Docs has an option where you can like draw. I don't.
make sure your name is on the lab report, please, and then pass that to the right side. Double check your name is on it. Pass it to the right side. All right, yes, now. All right, take a look here at the agenda board. We're getting actually towards the tail end now of this long unit on dynamics, chapters 4 through 6. That means that the next exam is on the horizon. Now, as I said to you previously, it is my own personal policy to not assign homework over Thanksgiving break. But you definitely want to do the extra credit project probably over Thanksgiving break, because when we return from Thanksgiving break, it's a horse race. We hit the ground running. It's 2 full weeks of instruction, then the last week, of course, is finals week. You have 2 exams in this period. The unit exam on chapters 4 through 6. It's not going to be until Monday, December 7th, but just a short 9 days after that is the final exam. So get some rest over Thanksgiving, because when we return, it's definitely a horse race. You know, last time in class, I introduced you to the law of universal gravitation. Remember that Einstein, remember that Newton didn't derive this expression. He literally intuited the mathematical form that gravity must take. The force that occurs between 2 objects of equal mass depends upon the masses themselves and the distance between them. You also got introduced to the universal gravitational constant last time in class. This is one of nature's fundamental numbers. It literally describes the force of gravity as it exists in the universe. A little bit later on today, I'll describe exactly how this was measured. At the very end of class last time, I used the law of universal gravitation to begin this process of unification. That is, showing the same physical principle describes the motion of a projectile near the Earth's surface. That's what I did at the end of class last time, and now it also describes planetary motion. So what we want to do here today first is the second step of this unification process, use the same physical principle to now derive Kepler's laws of planetary motion. When Newton did this in 1687, he did so with the full-blown calculus involving elliptical orbits of the planets as they orbit the sun. We're going to greatly simplify the situation, however. We'll assume that as the planets orbit the sun, they do so in uniform circular motion. This will allow us to come up with simple algebraic expressions for specifically Kepler's second and third laws. So let's take a look at the following. We're going to be walking in Newton's footsteps today. So in a simplified form, we're skipping our way past the calculus associated with elliptical orbits, use Newtonian gravitation to derive Kepler's second and third law. I will briefly refresh your memories as to what those laws were. Remember, however, when Kepler discovered them, he discovered them empirically from Tycho's data. We now basically want to derive those expressions. Okay, but first of all, recall Kepler's second law. That was a rather strange one, and I only briefly described in class what's called the law of equal areas. Remember, here's the basic description of that. what I'm going to do here is kind of greatly exaggerate an eccentric ellipse, like so, for a planet as it orbits the sun. Remember that the sun resides in the focus. And then what we do is we look at the planet as it moves in its orbit over some time interval, call that t. And now, as Kepler discovered from Tycho's data, when a planet is close to the sun, near perihelion, if you remember that term, this is when it's moving fastest in its orbit. So in a time t, it will say move from here to here on my diagram. As the terminology goes, it sweeps out an area like so on the ellipse. And then we look at the planet when it's, say, on the other side of the sun, close to aphelion, that's its furthest approach, and it then is therefore moving slowest in its orbit, as discovered by Kepler through Tycho's data. So in the same time interval t, it may say only move from here to here. But the area that it sweeps out on the ellipse like so, as Kepler discovered, is exactly equal to, say, this area over here, the law of equal areas. To kind of strip it down, however, to the most simplest possible description, essentially what Kepler's second law is saying is the closer a planet to the sun, the faster it moves. So in a very simple way, we want to show this relationship here now mathematically by using the law of universal gravitation. Remember, by the way, as far back as Copernicus, more than 100 years before Newton, Copernicus made this assumption just to fit the appearances that we see in the heliocentric universe as the planets orbit the sun. Copernicus just kind of made that assumption and went from there. Now we want to see physically why that is. So in this simplified derivation, we now have, for example, a planet in uniform circular motion as it orbits the sun. So the sun, we'll say, is here. It has some mass, and the sun. And then right here is the planet. Let's just say that it has mass m. The two objects are separated by a distance here. Call it r. That's the radius of this orbital circle. It's the same thing as the semi-major axis of the ellipse in the elliptical orbit. Okay, now, according to Newton, there's only one force here exerted on the planet, and that's the force of gravity. And then therefore, that force of gravity is going to give us, in this case, a centripetal acceleration inwards towards the center of this orbital circle, inwards towards the sun. So when you write out F equals ma here, this is actually the exact same way that we always write it for a situation where an object is in uniform circular motion about another, that is, as this planet, for example, orbits the sun. So we have the force of gravity, g times the mass of the sun times the mass of the planet, divided by the distance squared. This then equals mass times acceleration. So this is the F in F equals ma. And then the mass times acceleration is mv squared over r, because the acceleration is a centripetal acceleration. So this is the opening step whenever describing an object orbiting something else in uniform circular motion. The same things always cancel. The mass of the planet, in this case, cancels like so, as does one of the distances r, here and here. And now to just come up with a very simplified version of Kepler's second law, all that I'm going to do is solve for the speed v. That's the orbital speed of the planet as it's orbiting the sun. So just take the square root of both sides, and you end up with this. And notice that all this expression simply says is that if you make r smaller and smaller, then the orbital speed v increases. That's basically saying mathematically what I wrote here in words. The closer a planet to the sun, the faster it moves. This is a very bare bones description, if you will, of Kepler's second law, essentially saying what happens when a planet is close to the sun. And then we get to Kepler's third law. Once again, I'll refresh your memories as to what that was. Kepler's third law was a very simple relationship between two very important numbers: the sidereal period of the planet, how long it takes to go all the way around, and the semi-major axis of the orbit. As we originally saw it, however, a couple of months ago, we wrote it out in the following way. So now this is Kepler's third law. We originally saw it as p squared equals a cubed, where p was the sidereal period. It was measured in terms of years, and A was the semi-major axis of the orbit. That was measured, if you recall, in terms of astronomical units. Once again, Kepler found this relationship empirically from Tycho's data. We now want to derive it using the law of universal gravitation. It's actually just a couple of steps. In order to derive here Kepler's third law using the law of universal gravitation, let's just back up to this blue step right here. Instead of solving for the speed v, as I did for Kepler's second law, let's instead come up with a relationship for the period. Remember, the speed of an object in uniform circular motion is equal to the circumference of the circle divided by the period. There is a notation change here now, however. When we originally saw the sidereal period a couple of months ago, we wrote it as p. But that's now the t. That's the period of this motion as this planet orbits the sun. And then we saw the semi-major axis earlier as a. That's now the r. That's the orbital radius of this circle in this simplified derivation. So what I now have to do using this notation is derive t squared is equal to r cubed. That's how we're now beginning to see it here. In order to find that relationship, as we'll see, it's just actually a couple of steps. What I'm going to do is take this expression for the speed v and plug it into here and square the terms. When I do, let's be careful, we already canceled out a distance r here from earlier. It canceled out with an r over here. So when I substitute this into the right-hand side, I now start to get the following. First of all, the left-hand side, g times the mass of the sun over r equals then v squared. So square all of these terms. So 4 pi squared r squared over t squared, like so. And now I'm just going to cross multiply and solve for t squared. So what I'm going to do, I'll take the t squared and just move it up here to the left. I'll take the g and the mass of the sun, move it down here to the right-hand side, and I'll take the r and cross multiply it up to here to get an r cubed. When you cross multiply the stuff around, you end up with this. So, take a look at that expression carefully. It says that t squared is proportional to r cubed. So, however, if we measure the t appropriately in years and the r appropriately in AU, in other words, if we're in the correct units, what should this number here be? Just take a look at Kepler's third law as Kepler first saw it. T was in years, r was in AU. So if we come to here, what should this number here in parentheses be if the t is measured in years and the r is measured in AU? Yeah, it should be 1. This guy right here should be 1 in the correct units. So let's see if it is. In order to see if that number is 1, what I'll first do actually is take the r cubed here and just move it down to the left-hand side. Rewrite the expression briefly just like this. So, and now we come to some numbers. What are those numbers? Well, first of all, we have, once again here, capital G, the universal gravitational constant. A little bit later on today, I'll go through exactly how it was measured. I'll show you how it was measured. But the number itself, if you remember from last time, is quite small. It's 6.67 times 10 to the minus 11 with these funky units, Newton meter squared per kilogram squared. And then we get to mass of the sun. How do we know the mass of the sun? Well, in order to find the mass of the sun, you actually need another number. and that's 1 AU. Not written out as 1 AU, because it's just 1 by definition, but exactly how many miles or how many kilometers 1 AU is equal to. Once you have that number, then you can use the law of universal gravitation, much like we're doing here, to actually measure the mass of the sun. But you need to know what 1 AU is. So in order to find the mass of the sun, you need to know what 1 AU equals in meters. So how was an AU originally measured? Well, as you might imagine, it's actually difficult to do. You have to wait for the right moment. You have to wait for a very rare event. Approximately twice per century, either the planets Mercury or Venus passes in front of the face of the sun as seen from the Earth. This is actually a very rare event. It's kind of like an eclipse, if you will, but it's referred to as a transit. A transit of Mercury or a transit of Venus only occurs roughly twice per century. In the 18th century, there were 2 transits of Venus that occurred 8 years apart. One in 1761, and the other in 1769. During both of those 2 events, the major European powers sent scientific expeditions around the world to record the event. And the reason for that is because, very simply, if you watch a transit of Venus, say, from 2 locations on the Earth at the exact same time, you can then use a little bit of parallax to ultimately measure what 1 AU is. Without going through all the gory details, here's kind of the basic idea. Take a look at this little diagram right here. So on the right-hand side of the diagram is the Earth, and then right here is the planet Venus passing in front of the face of the sun as seen from the Earth. You basically just watch the transit from 2 locations on the surface of the Earth. You say stand here, and you see the position of Venus against the face of the sun in this direction. You have another guy over here, he looks at the exact same time at the planet Venus, he sees it against the face of the sun in this direction. Using some geometry, you can figure out what the parallax angle is, and then if you know the distance between your 2 locations here on the surface of the Earth, ultimately you can find the distance from the Earth to the sun, an AU in terms of, say, meters. This was done successfully for the first time in the 18th century during the transits of Venus in 1761 and in 1769. And as I mentioned, transits of Venus are quite rare, but one of them actually happened a couple of years ago. You guys, I think, were maybe in 8th grade at the time. How many of you remember hearing about that event, a transit of Venus? A couple of you are nodding. It actually happened one afternoon right after school. It literally happened right in the middle of 7th period. So after the day had ended that day, we actually all went outside with my telescopes and we watched the transit of Venus. It takes several hours for the actual transit to occur. So if you happen to be one of the lucky ones to see that transit, you were in fact very lucky, because the next one is not going to happen for more than 100 years. The next transit of Venus is not going to happen until the early 22nd century. So if you did happen to see it a couple of years ago, congratulations. That was basically your one shot. Unless, of course, we all become immortal through the singularity, right? But that was basically your shot at it. When that measurement was first made in 1769 and then 1761, we now know what 1 AU is in terms of meters. So that's how we originally measured it, basically by doing this parallax calculation. So the answer to the question that I just erased for here is, how was an AU measured? You have to watch the transit of either Mercury or Venus. This is how it was originally first done. This then led to the following number. 1 astronomical unit, and I've mentioned this before, is about 150 million kilometers. It's about 93 million miles. It's 1.5 times 10 to the 11th meters. That's how we know that number. Once we did find this number, then we could use the law of universal gravitation to find the mass of the sun. The mass of the sun is about 2 times 10 to the 30th kilograms. So that's how we know what the mass of the sun is, by determining this number here. And now going back here to this coefficient, if you will, in this Kepler's third law calculation, let's now plug into the right-hand side of the expression, capital G and the mass of the sun, and let's see what we get. So this is going to give my calculator here a workout. What you will rapidly discover, by the way, is that chapter 6 is going to really give your calculator a workout. So let's see, multiply squared, and then divide by G, and then multiply here by the mass of the sun, which is 2 times 10 to the 30th kilograms. So after you calculate this out, you end up with a number that is nowhere near 1. I end up with something really tiny, 2.96 about times 10 to the minus 19. But I'm in metric SI units. So what are the units of this number? They are seconds squared per meter cubed. I'm in the wrong units. Time has to be in years, and the distance has to be in AU. So I have to convert. Now, by the way, when it comes to some of these crazy numbers that you're beginning to see in these problems, these crazy conversion factors that occur in these problems, you of course do not have to memorize any of these numbers. They're all going to be provided for you. As you work through some of the example problems, however, in chapter 6, there are some of them that you're probably going to start remembering. So first of all, we have meters. I have to convert it into AU. This right here is actually my conversion factor. So let me just go ahead and use that. So now I'm going to multiply by the following. Quantity, 1.5 times 10 to the 11th meters cubed over 1 AU cubed. And then I have to convert seconds into years. I've mentioned this before, but there's about 31.5 million seconds in a year. 3.15 times 10 to the 7th seconds per year. So using that conversion factor, once again, you don't have to memorize it or anything. I now multiply by the following. 1 year quantity squared per 3.15 times 10 to the 7th seconds squared. Like so. Now watch what happens here with the units. I first of all have meters cubed, canceling out with meters cubed. Like so. I have here seconds squared, canceling out with seconds squared. Like so. And then all that's left are years squared per AU cubed. So I'm now going to get some number in the correct units. Years squared per AU cubed. Let's see what it is. So I still have this weird number here in my calculator, and now I'm multiplying by 1.5 times 10 to the 11th raised to the third power. Times 1.5 times 10 to the 11th raised to the third power. And then I take that and divide by 3.15 times 10 to the 7th squared. So divide by 3.15 times 10 to the 7th squared. And I end up with, and it's out to a couple of decimal spaces, what? So I end up with, yes, t squared is equal to r cubed as long as the t is measured in years and the distance is measured in terms of astronomical units. This is the second part of the unification process. I used here the same physical principle, the law of universal gravitation, to show that planetary motion is the same thing as an object moving in free fall, say, near the surface of the Earth. As convincing as these calculations are, however, it's still not good enough. That is, you have to provide a precise numerical example for the theory of gravitation to show, in fact, it's correct. Remember that last time in class I mentioned the following phrase to you. I said that Newton precisely and mathematically shows that Newtonian gravitation works. The key word there is precisely. You do have to show a precise numerical example. Newton does in Principia when he publishes in 1687. And it has to do with the orbit of the moon around the Earth. Let's take a look at his proof. Now, when Newton submitted his proof in 1687, he did so by assuming that the moon orbits the earth in an ellipse. It does. He went through all of the gory details of the calculus to show the proof of his theory. However, we'll once again simplify. We're going to assume that the moon orbits the earth in uniform circular motion, and when you do, you get the exact same result anyway, as we'll see. So part A of the problem here is the theoretical prediction. Show that Newtonian gravitation predicts that the moon falls 1/20th of an inch per second. Now, 1/20th of an inch, that's an exceedingly tiny distance. That's, like this. I'm barely pinching my finger here and thumb like so. That right there is about 1/20th of an inch. What we want to show is that Newtonian gravitation predicts that the moon falls this distance in 1 second. But how do we picture the moon as falling? This was a very difficult concept for people to wrap their heads around 350 odd years ago. He provides, first of all, before he actually does the proof, a simple conceptual example. I described this example to you a couple of weeks ago. Newton literally drew this out in Principia. So how, I guess I should say, how do we picture the moon as falling? Well, recall the following description. It kind of links together conceptually motion near the Earth's surface and motion in heaven. We have the Earth like so, and then we just throw a projectile near the surface of the Earth. It falls after moving some distance. They throw it a little harder, moves further after falling like some distance like so. But if you throw it hard enough, as it falls, the Earth's surface curves away from it, and the object ends up in orbit about the Earth. So I've given you this conceptual example before. Newton literally drew out this diagram and explained it prior to actually calculating out the proof. Just driving home the fact that motion near the Earth's surface and motion in the heavens is the same thing. So we kind of get that description out of the way, but there's still a little bit of a problem when it comes to this actual numerical example, this proof. Newton didn't know what the value of capital G was, the universal gravitational constant. He just assumed that it existed and kind of went from there. As we'll see a little bit later on today, it actually wasn't successfully measured for the first time until a couple of decades after Newton's death. So then how does he get around this problem of not knowing capital G? Well, he basically just sets up a ratio. Here's essentially what he does. So part A here is the theoretical prediction. But what he does first is he says, okay, let's first calculate the distance, then an object will fall in 1 second. If dropped from rest near the surface of the Earth. It is. So here now is that calculation. Let's picture first of all the Earth like so. Okay, once again, remember from last time in class, we can treat the entire mass of the Earth as a point at the geometric center. Like so. Call that M sub E. Okay, and then we've got the marker in free fall near the surface of the Earth. So here's the marker. Like so, of mass M. Remember, for all practical purposes, is that as long as it's near the surface of the Earth, the distance from the marker to the center of the Earth is just the radius. So, and now we just set up F equals ma. Once again, there's only one force exerted upon the marker, and that's the force of gravity. So F equals ma then, like I did at the very end of class last time, is just the following. The force of gravity, gmm over distance squared, equals mass times acceleration. The acceleration we also know is small g, and that was measured 50 years earlier by Galileo. This is an English units problem, so we have to think of small g as 32 feet per second squared. So this dates back to Galileo. Okay, now the mass of the marker cancels out, no surprise, and then we just end up with the result that we saw at the end of class last time. But now, yes, as Jacob correctly pointed out a few minutes ago, if we go back to chapter 2, it's now just a little bit of free fall kinematics. Without going through all the vectors and all that stuff that we went through back in chapter 2, if you take an object and just drop it from rest like so, the distance that it falls is just 1/2 gt squared. So let's call that distance then d. So the distance that the object falls is 1/2 gt squared, where the time t is just 1 second. And g, as measured 50 years earlier by Galileo, is 32 feet per second squared. So 1/2 times 32 times 1 squared is just 16 feet. And now we go to the moon. So now we calculate how far the moon falls in 1 second. How do we even begin to think of the moon as falling? Well, consider it like this. So here's the moon now in uniform circular motion about the Earth. Right here is the Earth. Once again, it has a mass m sub e. And let's say that the moon happens to be right here on my diagram when I look at it. It has some mass, we'll just call it m moon. The distance from the Earth to the moon, we'll just refer to here as r. Now at this moment, let's think of the moon as moving clockwise on my diagram. So at this moment, it's basically moving in this direction, like so. But now begin to think of the moon as a projectile. Remember how I kind of described a projectile to you when I did the monkey hunter demonstration? I described the projectile as falling. It's falling below a line that it would have moved if there was no acceleration. So with respect to that demonstration, remember kind of how I had it set up? The gun was over there on the 3rd row desk, and the target was up on the ceiling. Remember, the gun was aimed directly at the target up on the ceiling. If I fire the gun and the projectile doesn't accelerate, it just moves along a straight line like so. But instead, the projectile is falling. It's falling below that line. Think of the moon as a projectile. The moon is falling below this line. We want to calculate how far it will fall below that line in 1 second. In order to do this, we once again just set up F equals ma. So to do that, there's only one force exerted here on the moon, and that's the Earth's gravity, like so. That then gives us an acceleration. Let's just call the acceleration a moon. So when I write F equals ma here then, I'll now have the force of gravity, gmm over distance squared equals ma. So, and the mass of the moon cancels out. So the acceleration of the moon then, therefore, is equal to the following number. And now here's where the ratio comes in. The distance r. That's the distance from the moon, to the Earth, to the moon. We've known that distance for almost 2,000 years. It was first measured by Ptolemy in the 1st century AD. Now, when I lectured on Ptolemy's calculation a couple of months ago, It was a precise calculation using parallax, the actual distance from the Earth to the moon. Ptolemy's result was very accurate. I phrased it to you in the following way. It was some multiple of Earth radii. And at the time, I said that that number would become extremely important in class one day. This is that time. Does anybody remember how many Earth radii away the moon is? Fourth period got it. Second period got it. Danny? 60 Earth radii. That's the distance that the moon is away from the Earth. Every now and then, numbers kind of come back to haunt you in this class. That's one of those numbers. It's 60 Earth radii. How does this help us? How does this help us? Watch this. So the acceleration of the moon then, therefore, is first of all the numerator, and then divided by now small r squared. Danny, did you have some help on that?
No, I said 16, not
You'll-
16.
I thought you said 60. I'm going to give you the benefit of it.
Grateful.
So small r is 60 Earth radii. Now 60 squared here in the denominator, that's 3,600. So you end up with this. Like so. We know what this is from the top board. Small g. So the acceleration of the moon, then therefore, is 1/3600 small g. Now, just to summarize, by the way, what it just took me the better part of 10 minutes to do, basically all that I've done is the following. If you're at the surface of the Earth and you're 1 Earth radius away from the Earth's center, acceleration due to gravity is g. However, if you go 60 times further away and gravity obeys an inverse square law, then the acceleration due to gravity should be 1/60 squared of its value here at the surface of the Earth. And it is. It's 1/3600 of g. So that's just what I did in the last 10 minutes, summarized into a couple of sentences. So then, therefore, the distance that the moon falls below this line can now be easily calculated. Once again, think of the moon as a projectile. It's essentially being launched horizontally on my diagram, and it's falling below that line. So then therefore, the distance that it does fall below that line is just 1/2 AT squared. So the distance that it falls, we'll call it d moon, is 1/2 acceleration of the moon, t squared. Or once again, the t here is 1 second. But we now know what the acceleration of the moon is. It's 1/3600 of g. And now if I just kind of rearrange these fractions a little bit, what we end up with is this. 1/3600 of 1/2 gt squared. The 1/2 gt squared, however, is 16 feet. So the distance that the moon falls then, according to the theory, in 1 second, is 1/3600 of 16 feet. So let me calculate what that is. So I just take 16, just divide that by 3,600. You get a tiny amount, as you might imagine. And that works out to be about 0.0044 about feet. And now I'll convert that into inches. Multiply by 12 inches per foot. Feet cancels, and we now end up with a distance in inches. Times it by 12, and 0.05 inches. That 0.05 is 1/20th of an inch. So Newton's theory of gravity literally predicts that in 1 second, the moon is going to fall like that tiny distance, like so, 1/20th of an inch below this line. That's the theoretical prediction. But then the second half is, okay, what actually happens? We'll see that after we take a short break. Let's do that now. RJ, make sure you stay with me for the remainder of the period. Don't fall apart on me.
I didn't know.
Last year, I fell asleep and you woke up and you're like, what the? He like went all
Stay with me, Brian. We're walking in Newton's footsteps. This is your opportunity to see his genius. This is your opportunity to see his genius.
See his genus? You're going. Guys, that was the most pointless shirt I've ever taken. Show me Staples. Oh wow.
You still have that orange sticker on? Of course it is.
You know what? I get it out there. No, Michael wakes me up.
Oh my god, it looks so overwhelming.
Time to show up on the
Refrigerate this when I get home.
Send somebody to chat while you're walking your stories.
It's a new filter.
Try it on.
Who's the best? Okay, but like,
Russ, there's actually an Afghan restaurant.
how many years is that?
I may have.
2010.
6 years once. There's a really good one.
This picture is so fantastic.
Oh, is it okay, actually, I'm fairly close to my parents. They were saying, who would you? Yeah, so like a year. Over here. Over Blake. Yeah. Mike, you guys. That's like long.
Is this a pink pen? Is it pink?
No, it's just a pink pen, but it's not pink.
It is pink. It looks stamped.
When's your
Carlos Hyde's injury.
Two. What?
He like 95 yards.
Yeah, I said that I should.
I'm so happy we're together.
99. Me too.
I'm so happy. Now I can just not
But I know my shoes.
That was so I felt it. I sent.
You were like going.
Wait, listen. I sent.
What are you gonna adopt a dog?
It was so stupid. I was wearing socks and I really was getting it.
Register and like get back. We're like, I don't know. It was like in the bushes. Wait, Mike, how are you gonna find this dog again? That was someone.
I have an A now. I have a 95.
they let it out. It's not like, I don't think it's
Can you take it? Yes. Yes. You're supposed to report it. You're supposed to not claim the 30 days.
I know, really.
Yes. Yes. That's right. Yeah, but like, that's the law.
Want to bet, dude? $30, like $30 for 30 days. One day. And betting technically also gambling's like illegal. Yeah, but we're not under the territory. They have so many chances to like.
Why?
Oh, really? Oh, really? So the guys were like, you guys put their gun to their head and they're like, you almost simulator die. So many chances.
Oh, you looked it up. What happened?
I do, I just did
Like, be honest, if you were one of those similars, you would have taken all their answers. Be honest, I would.
I'm posting this one.
No. Yeah, I swear to God. I would kill you. I would ask my I was going to sit down and I just sat down and like, she's like, how the hell did I do that?
It's distorted. You can't do it again. It's distorted. It's just her face.
All right, everybody, please take your seats.
Did you guys have to do over this? Remind me of your house to show you your voice.
Oh yeah, he told me that.
It's so funny. It's her little sister like holding a dog. What? And her little sister's like, what? Like
So the theory predicts that the moon falls literally that distance in 1 second, 1/20th of an inch. So now the question is okay, well, what really happens? Well, in order to calculate what really happens, we just need two numbers in Pythagorean theorem. The two numbers have been known since the time of antiquity. First of all, the distance between the Earth and the Moon, 60 Earth radii, and the Moon's sidereal period, how long it takes to go all the way around the Earth, 360 degrees. That time, by the way, is not a full set of lunar phases. A full set of lunar phases is a synodic period. That's about 29.5 days. The sidereal period is just over 27 days. We need that number along with the distance from the Earth to the Moon to show what actually happens. That's part B. So using the Moon's orbital data, show that observations match the theoretical prediction, that is, show that Newton's theory of gravitation is in fact correct. Okay, so here's how we start to get a right triangle out of all of this, and then just use a little bit of Pythagorean theorem. So now here's part B. So here's the circle representing the Moon's orbit about the Earth. Here's the Earth. Once again, let's think of the Moon as being right here. So the first leg of the triangle is this distance right here, the radius of this orbital circle, small r. That's the 60 Earth radii. However, we need it in terms of inches. So how many inches is 60 Earth radii? Well, I have it written down for us. As you might imagine, it's pretty big. It's 151,338,528,0 inches.
One more phone number.
Yeah, right there. So that right there is 60 Earth radii in terms of inches. So if you're ever curious, it's that distance. And then the other number that we're going to need here to begin to construct a right triangle is the Moon's sidereal period, capital T. And as I said, it's not the same thing as a full set of lunar phases, which is a synodic period, just over 29 days. The sidereal period is a little bit less than that, it's just over 27 days. And we need that number in terms of seconds. I've written it down for us as well. It's 2,360,590 seconds. 2,360,590 seconds. So this is the orbital data that's being described in this problem. We've known these two numbers for a very long period of time. Okay, now how do I get a triangle out of all of this? Well, if I think of the moon, remember, as moving clockwise, say on this diagram, in 1 second, the moon would move some linear distance. Think of that linear distance as a line, like so. And let's call that line here a distance s. So s is the linear distance. The moon moves in small t equals 1 second. So how do I find that distance? Well, that distance is just equal to the speed of the moon multiplied by that times small t. The speed of the moon is its circumference divided by its sidereal period. So let's go ahead and calculate that number. It'll be in terms of inches. So what I have to do is I go 2 pi times this huge number here. 2 times pi times 151, 338, 151, 338, 52800. And then divide by the orbital period, 2,360,590 seconds. 2,360,590. So, multiply by 1 second, and you end up with 40,282 inches. So if you were ever curious in terms of inches, how far does the moon move in 1 second? It's that distance. Okay, now completing this right triangle on my diagram here is the hypotenuse, like so. The hypotenuse is the combination of two things. Right here is once again the orbital radius. This right here is just the r, like so. And the right here is what we're looking for. That's our unknown. That's the distance that the moon falls below this line in 1 second. Let's call this d moon. And so now to calculate d moon, it's just Pythagorean theorem. So from Pythagorean theorem on my triangle, I'm going to first of all have the r squared plus s squared equals the hypotenuse squared. The hypotenuse is the sum of r and d moon. And now we just solve for d moon. So to solve for d moon, what I'm going to do here on the right-hand side of the expression first is I'm going to FOIL this. I'll do this for us fairly quickly. So if I FOIL this out here, I'm going to have r squared and r times d moon, but there's two of them. So, and then plus d moon squared. And then before I do the last step here to solve for d moon, we could actually simplify this a little bit. Take a look at this term right here. Remember what d moon is predicted to be. It's predicted to be 1/20th of an inch. So then therefore, how big is this number here compared to r, gigantic number up there on the top board, and compared to s, this gigantic number over here on the far right-hand board? In other words, what can I say about d moon squared? It's basically negligible. So then therefore, all that remains is right here. So to find the d moon now, the first thing I'll do is subtract out the r squared from both sides, like so, and then just take the remaining s squared here and divide it by 2r. So then therefore, the actual distance that the moon falls is s squared over 2r. And now let's see what happens. So I still have s here from earlier in my calculator, so now I just square it, like so. And then divide by 2 times 151,338, 52800. I end up with, in terms of inches, 0.05 inches. It's 1/20th of an inch. The fact that this number what really happens matches that number, what the theory predicts, what does that then tell us about Newton's theory of gravitation? It is, in fact, of course, correct. And now because all of us here are in the presence of the long-dead master, and what he did 3.5 centuries ago, you still have to show your proper respect for exactly what it was that Newton did. So yeah, Newton's theory of gravity is in fact correct. However, if you think about it very carefully, before I get to that, Danny, your question.
Never mind, it's on.
Okay. Before I get to that, however, before we go any further, think about very carefully what Newton's theory of gravity is in fact saying. If you think about it carefully, it looks and smells like magic. Because basically Newton is saying this. You've got the sun here, say, for example, and you've got the earth here, and they're separated by 150 million kilometers of nothing. There's nothing there. It's completely empty space, 93 million miles of nothing. Yet somehow, almost magically, the sun is able to instantaneously reach across that distance, exert a force on the earth, keeping the earth in its orbit as it orbits the sun. If you think about that carefully, that looks and smells like magic, and Newton was well aware of this. One of the purposes, by the way, of the scientific revolution, which is obviously embodied here in the presence of Isaac Newton, essentially, is that it was to finally forever cast out of the study of the natural world religion, magic, and the occult. That's basically what the purpose of the scientific revolution in part was to do. But then Newton comes along and he introduces into science his theory of gravitation, and it looks and smells like magic. Newton's defense of his own theory was simply this. There is a very famous quote attributed to Newton in this context. He said, "I feign no hypothesis." What he basically meant was this. He says, regardless of what gravity may be at a fundamental level, it behaves this way mathematically. And it makes predictions, such as this problem. Predictions that can be tested. And it passes those tests every single time. And that's basically as far as he goes. Whatever gravity may be at a more fundamental level, it works this way mathematically, and that's as far as Newton got. So if you want to think of it this way, here's a very good way of thinking of it. Think of Newton as the guy who invented physics. He basically unified together projectile motion and planetary motion with the law of universal gravitation. That represents the birth of modern science. So he basically invented physics. But then 2.5 centuries later, somebody else comes along and reinvents physics. Who do you suppose that was?
Albert Einstein.
That was Albert Einstein. We'll get to him at the end of the year. The remainder of chapter 6 is application. That is, just apply the law of universal gravitation to various situations. Because it is universal, that means that we truly can apply it to the universe at large, and we can actually begin to tackle some really big questions with the law of universal gravitation. When we return from Thanksgiving, by the way, this is my opportunity to throw as much astronomy at you as I possibly can. That's what I'm going to do when we get back from Thanksgiving. However, there is still one minor detail left before we get to all of that, and it has to do with capital G. How is capital G first measured? So let me give you a basic description of that, then I'm going to show you a short film clip of the actual experiment itself that was first used to make the measurement. Because capital G is so small, it's actually pretty difficult to measure. And I speak from experience because I had to make a measurement myself, for example, when I was a physics student in college. The first person to successfully measure capital G was an Englishman who lived a little bit after the death of Isaac Newton. Isaac Newton died, I believe it was 1732. The actual experiment that was first performed to accurately measure G didn't occur for about another 50 years or so. So we're talking about the late 18th century here. The person who made the measurement was an Englishman named Henry Cavendish. the experiment itself is just referred to now as the Cavendish experiment. And this is a few decades after the death of Isaac Newton. This is the late 18th century. The Cavendish experiment uses a specific type of pendulum. It's called a torsion pendulum. The idea of a torsion pendulum, however, is pretty simple. Basically what it consists of, in this case, is just a long stick that is hanging from a wire from the ceiling, such that the stick could twist sideways back and forth like this. This type of pendulum is referred to as a torsion pendulum. That was with the Florida. Now, as seen from the side, the pendulum itself, by the way, as Cavendish originally did it, was huge. He did it in a big laboratory. It was basically as big as a gymnasium. And he had this huge iron bar hanging from a wire that was about 10 feet long. And then on either sides of the iron bar, he then attached to the iron bar large lead balls. Lead is a very dense, heavy metal. So he then hung it, and then from the side, it basically looked something like this. Here's a side view. So you've got this long iron bar like so, hanging from a wire. On either sides of the iron bar like so, he placed some masses. They were basically dense metals. And we'll just call them mass M. They were the same. Okay, then, on the floor below, next to the pendulum, he places two identical stationary masses. So there's a mass here, called a capital M, and over here is an identical stationary mass, capital M. Now, this is what the pendulum apparatus looks like from the side, but if you were going to look down on the pendulum, say a top view, it looks like this. Here's the pendulum like so, with the two masses M like this, and the wire is pointing straight out at us like that. So here's the wire, like so. Okay, and then the stationary masses off to the side in red, they're actually positioned diagonally across from each other. The one over here on my left is positioned right here. And it's positioned such that it's closer to this side of the pendulum than this side. And then the other one over there on the right-hand side, that's actually positioned right here. That's positioned so it's closer to this side of the pendulum than this side. And then what you do is you just set this pendulum up. This is kind of like your starting position, if you will. And then you just let it go. And what is then going to happen? Well, there's going to be a very minute force of gravity exerted upon this side of the pendulum due to this mass, like so. There's going to be a very minute force of gravity exerted on this side of the pendulum due to this mass, like so. And then very slowly, it's so slow you can't even see it move. The pendulum begins to swivel. It does this. It overshoots the masses, slows down, stops, comes back, overshoots the masses, slows down, stops, come back, and it begins to oscillate like so. However, every time that it oscillates, the degree of oscillation, what's called the amplitude, gets smaller and smaller. The pendulum executes a specific type of motion. It's called damped harmonic motion. We'll study it briefly in the second semester. By the time of the late 18th century, however, damped harmonic motion was well understood. When the experiment is over, the pendulum ends up at rest, like so, diagonally across, like so, from the masses. So the details of this motion actually allow you to calculate how much force is exerted upon the pendulum. So the pendulum executes what is called damped harmonic motion. How that motion occurs determines then the force that's exerted on the pendulum. And now just take a look at the law of universal gravitation in its simplest form. So on the left-hand side of the expression is the force, which you can calculate from the motion of the pendulum. The motion of the pendulum gives you this. And then take a look at the right-hand side of the expression. Specifically, take a look at these guys right here. Those are all experimental controls. You know all of the relevant masses. You know all of the relevant distances. You set that up ahead of time. So this stuff here in the box, you know all of this. These are experimental controls. So if you know all that stuff, and the motion of the pendulum gives you this, what's the only unknown in the expression? Capital G, which you can then measure. So you can now find. That's the basic idea behind the experiment. It's essentially using a pendulum to measure capital G. It is, however, a very difficult experiment to perform, as Cavendish originally did, because capital G is so small. And I speak from experience because I've performed the experiment myself. Whenever you major in one of the sciences or a related field, such as engineering, usually one of the courses that you have to take as an undergraduate is what's called advanced laboratory. What you basically have to do is, within your discipline, you have to repeat all of the classic experiments that were done in that discipline. So as a physics major, I had to do the Cavendish experiment. If you were going to be a biology major, for example, you would take a similar class. One of the experiments that you would have to do would be like the Miller-Urey experiment. Remember that, say, from AP Biology or Honors Biology? You would basically have to do that experiment. Unlike this class, however, where I'm not so concerned with your percent error, in that class you have to get less than 1 or 2% error, or you fail the experiment and you have to do it again. Usually, by the way that this class is set up is that it actually never formally meets. You just meet once at the beginning of the semester. They give you the list of experiments that you have to perform. They tour you all of the facilities and the laboratories that you can use to do the experiments. And then you basically have to do, I think it's like 5 or 6 experiments, something like that, over the course of the semester. And you have to get less than 1 or 2% error, or you fail the experiment. You could try as many times as is necessary. So we actually had to perform the Cavendish experiment twice. The first time that they had us do it was exactly as I described, kind of on a large scale as Cavendish originally did. We had this huge torsion pendulum in this laboratory room. It was like 10 feet long, something like that. When we did the experiment, however, we noticed very quickly that it was easy to introduce error into the experiment. Because the mere act of you walking through the laboratory, the vibrations of your footsteps, that's enough to throw off the motion of the pendulum. Just the air currents that you generate while walking through the lab, that's enough to throw off the motion of the pendulum. So once we figured out how to do this by eliminating the errors, what we essentially had to do was set up the experiment and then basically leave the room immediately. And we went to an adjacent office, and inside the office there was a plate glass window so we could watch the pendulum. However, as I said, the pendulum is swiveling so slowly you can't see it move in real time. So what we would do is we'd sit there and do our homework, blah, 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 and then look up at the pendulum and we would see it like that. And then we would look down for another 10 minutes and do our homework, blah, 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 look up again, and the pendulum had noticeably moved. It was kind of eerie. You guys remember that scene in The Shining where the bushes are like getting closer and closer to him, but he can't see the bushes moving? It was kind of like that, because you would look at the pendulum like that, you look down for 5 minutes, you look back up again, and the pendulum is slowly moving. So we ultimately were able to work out all the kinks of doing the experiment this way and get a good result. After we did that, however, they had us do it again, but in this case, you do it on a small scale. If you do it on a small scale, which is what the ex-presidents will do here in the film for us in just a moment, it's actually fairly easy to do. So here's the film clip using the ex-presidents of the Cavendish. I have to prepare my screen. the ex-presidents, remember them? They're kind enough to do the Cavendish experiment. When you do it on a small scale as they did here, it's actually fairly easy to do. Still takes a long time to do it because the motion of the pendulum itself is so slow. But if you set it up like this, it's fairly straightforward. All right, so the measurement of capital G. Okay, so what they do is they set up their pendulum right there in that little box, right there. It's basically a box that's encased in glass, and then you take all the air out of it, so there's no air resistance. Okay, now what they're actually doing here is they're shining a light onto the pendulum, and then right there at the top of the pendulum is a mirror, like so, which then reflects the light into the distance onto a meter stick that they have in the background. This allows you to measure, so for example, the pendulum's position. Okay, now what you have to do is you have to set up the experiment first. The way that you set up the experiment is, in this case, they use large lead balls, which are a very dense, heavy metal, and you then put them directly across from each other on either side of the box. So one of the ex-presidents reaches in, like so. Okay, and then several hours goes by. During that time, the pendulum is oscillating back and forth, and at the end it lines up with those balls. That's when the experiment begins. That gives you the initial position of the pendulum. And then what you do is you reverse the position of the lead balls. And they then photograph the approach to the new equilibrium position. They do so at 80 times normal speed. So right there is their starting point. And then one of the ex-presidents will reach in just a moment and shift the position of the lead balls. And then they photograph it at 80 times normal speed. So now the experiment is set up, the pendulum is aligned with those balls, and now they just reverse the position of the balls. Don't disturb the pendulum when you do it, though. You learned that the hard way. Like so, and then they photograph the whole thing at 80 times normal speed. They'll show us this on the meter stick. Damped harmonic motion executes a very specific type of curve. What they're plotting here in this graph is actually the horizontal position of the pendulum as a function of time going downwards. Notice that the degree of oscillation, the amplitude of the oscillation, is decreasing as time goes on. Once again, this is all at 80 times normal speed, because take a look at the numbers there going downwards for the time axis. They're in terms of thousands of seconds. So we're talking about several hours here of motion. Once again, it's literally the force of gravity exerted on the pendulum that's caused by the large lead balls. And then the details of this graph could be used to calculate exactly how much force was exerted upon the pendulum. So once you know what that number is, you know all of the masses, you know all of the relevant distances in the problem. The only thing that's left is capital G. So when you do the experiment like this on a small scale, it's actually fairly easy to do. When we initially did it on a large scale, it took us a couple of weeks, multiple attempts to get a good result. Here, I think we were able to actually knock this out over the course of a very long afternoon. So if you do it like this, it's actually fairly easy to do. I'm just gonna let it finish. So the details of that curve, that then gives you the force. Ultimately, from that, you can figure out what it is. So that's how capital G was first measured successfully in the late 18th century by Henry Cavendish. Okay, come on. No fast forward button. Good enough. Right. And then, as I said, it's this point, just application. As we go through applications, the situations will get stranger and stranger. However, we'll start off with something rather easy. All I'm going to do today is one example. Let's just describe what happens when an artificial satellite orbits the Earth. That'll be good enough for today. So we're gonna have an artificial satellite orbit the Earth in uniform circular motion once again. What I'm actually gonna do here at the very beginning of the problem is just very quickly rederive Kepler's third law. Kepler's laws of planetary motion don't just apply to the planets orbiting the sun. They actually apply to anything that orbits anything else. In this case, an artificial satellite orbiting the Earth. Once you see the basic form of Kepler's third law, how it applies in various situations, when we do return from Thanksgiving break, we'll just use it over and over in increasingly bizarre and stranger situations. Pass this to RJ, please. And once again, all orbit types of problems such as this with uniform circular motion, they all very much begin exactly the same way. So here's how we'll picture this. We'll just go through the basics first, then we'll get to a numerical example down at the bottom here of the problem. So first of all, here's the Earth. Once again, we just treat the entire mass of the Earth as a point here at the geometric center. And then we've got an orbital circle like so for an artificial satellite, like a weather satellite or something like that. Our satellite will say it has a mass m. The distance between the center of the Earth and the satellite itself is just the orbital radius of the basic circle. Let's refer to it simply as r. And now, very quickly, here's the re-derivation of Kepler's third law. There's only one force exerted upon the satellite, and that's the force of gravity, but it gives us a centripetal acceleration inwards towards the center of the circle, inwards towards the center of the Earth. So when I write F equals ma, I just have the force of gravity, gmm over r squared, equals then mass times acceleration, a centripetal acceleration of v squared over r. So notice this starts out exactly the same way as the beginning of the period today when we had a planet orbiting the sun. This is always the opening step. The same things always cancel out. The mass of the satellite in this case cancels out, as does one of the distances r, here and here. And then, for a quick re-derivation here of Kepler's third law, we'll just substitute in for the speed v the following expression. Speed is equal to the orbital circle's circumference divided by the period. So I just plug that into here. I square each of the terms. Keep in mind that I've already canceled out an r, however, with the one that was over here. So now on the left-hand side, I have g mass of the Earth over r equals then on the right-hand side just v squared. 4 pi squared r squared over t squared, like so. Now we just solve for t squared. So take t squared and move it up here. Cross multiply the g and the mass of the Earth down to the right-hand side. Take the r and multiply it by r squared here to get an r cubed. An easy mistake to make, by the way, is to accidentally cancel an r here and here. That's wrong because this is in the numerator, this is in the denominator, so be careful of that. So when I cross multiply and solve for t squared, here's Kepler's third law. So once again, t squared is proportional to r cubed. The proportionality is always the same thing. It's always 4 pi squared over g times the mass of the object that's being orbited. In this case, it's the mass of the Earth. Earlier today, it was the mass of the sun. Kepler's third law always looks like this for an object orbiting another object as long as the object is in uniform circular motion. Very simple and straightforward. And now we apply it to a specific numerical example. When we do, however, it does ask us to get the period by itself in the problem, so I will go one more step here, of course, and take the square root of both sides. So the easiest thing to do it is just write the whole right-hand side underneath the radical square. And now notice how this mathematically behaves. If you increase the radius of the orbital circle, in other words, you get further and further away from the Earth's surface, you increase the altitude of the satellite, what then happens to the orbital period? it increases as well. So in other words, the further your satellite from the Earth, the longer it takes to go all the way around. And now we specifically apply it to a numerical example. The numerical example here at the end of the problem sounds a little strange, however. It's asking us to calculate this number, the orbital period, if our satellite is orbiting the Earth at an altitude of only 1 meter above the ground. Is it possible for me to take this marker, for example, and throw it such that it orbits the Earth at an altitude of only 1 meter above the ground? Yeah, it is, as long as it goes fast enough. We'll, by the way, ignore the Earth's atmosphere, so the marker won't burn up in the atmosphere. We'll say that there's no buildings or mountains in the way for the marker to run into. So then therefore, if I do throw the marker hard enough, as it falls, the Earth's surface will curve away from it. And we'll end up then in orbit around the Earth forever. So essentially, how long would its orbital period be if we could somehow do that? Yeah.
Like, how hard would that have to be thrown around?
You'll see, I'll calculate out the numbers. So the first thing I'll do is find the period, and then after that I'll find the speed. So to find the period, we now get to the numbers themselves. Okay, first of all, capital G, as originally measured by Cavendish, is this number here. And once again, when it comes to all of these crazy numbers that you're seeing in the problems today, and in the problems to follow next week after we get back from Thanksgiving break, once again, you don't have to memorize any of them. You don't have to memorize the strange conversion formulas or anything like that. Okay, from last time in class, I described to you the mass of the Earth. The mass of the Earth is 6 times 10 to the 24 kilograms. And then we get to the radius of the orbital circle. Essentially, our marker is basically at the surface of the Earth as it's orbiting the Earth. So then therefore, for all practical purposes, what is the radius of our orbital circle here equal to? It's just equal to the radius of the Earth itself. So I'm just setting here the radius of our orbital circle equal to the radius of the Earth. Once again, this is a known number. It's about 6,400 kilometers. It's 6.4 times 10 to the 6th meters. So those are now the numbers that I'm going to plug in to this expression here, essentially Kepler's third law, to calculate the orbital period. When I do, it's going to be in terms of seconds. After that, I'll convert it into hours. Capital T is now the following. So just working my way through, I've got first of all 4 times pi squared, times then the orbital radius, the radius of the Earth. 6.4 times 10 to the 6th, then raised to the 3rd power. And then divided by this stuff. Use parentheses when you do this yourself in problems. 6.67 times 10 to the minus 11 times 6 times 10 to the 24 mass of the Earth. And then don't forget to take the square root of the whole thing. When I do all of this, I end up with 5,085 seconds. And now to convert this into hours, there are 60 times 60, or 3,600 seconds in an hour. So if I divide out by 3,600 seconds in an hour, this is 1.4 hours. We've seen that number before. We saw it back in chapter 5 with a rather strange example involving the Earth. You spin the Earth faster and faster, eventually everybody becomes a projectile at the Earth's surface. That will occur if the Earth is rotating with a rotational period of 1.4 hours. I said this at the time. An object in that situation would actually be in orbit around the Earth like so, as the Earth is rotating with you. That's basically why this number here is the same as it was in that previous example. Yes, it's possible to orbit the Earth if the orbital period is about 85 minutes or so, right at the surface of the Earth itself. However, as you go upwards away from the surface of the Earth and you increase the altitude, as we described earlier, the orbital period increases as well. In low Earth orbit, which is a few hundred miles above the ground, say where the space station orbits the Earth, the orbital period of the space station is just over 90 minutes. So as you get further and further away from the Earth, this number here begins to increase. But in low Earth orbit, typically a satellite will orbit the Earth in about an hour and a half. In the case of the space station, I think it's like 93 minutes or so, something like that. And then Aaron asked me, okay, well, how hard would I have to throw the marker in order for this to happen? So let's calculate its speed. This would be the speed with respect to the center of the Earth, by the way, not the surface of the Earth, to be technical about it. But that speed would be equal to the orbital circumference divided by the period. Now, the period would have to be in terms of seconds here, 5,085 seconds. So 2 times pi times 6.4 times 10 to the 6 meters for the radius of the Earth, and then divide by 5,085 seconds. This comes out to be about 7908 or so meters per second, which is just under 8 kilometers per second. So if I threw the marker such that it had a speed of 8 kilometers per second, technically it's in orbit about the Earth. If there was no atmosphere, if there was no mountains or anything like that for the marker to run into, it would come back into this room 5,085 seconds later, about 85 minutes later or so, we would have the marker come back here into the room, 5,085 seconds. Okay? All right, that's good enough. Let's take a look here once again at the agenda board. I remind you that over Thanksgiving break there is no specific homework. But yes, you definitely want to do the extra credit over Thanksgiving break. Get it out of the way, because when we return from Thanksgiving break, we hit the ground running. Get some rest over the next 9 days. Forget about this place. Believe me, I sure as hell am.